Welcome back, everyone. In this video, we're going to continue learning more about quantum numbers and how they relate to orbitals. We're going to learn about what it means for an orbital to be degenerate. We're going to talk about nodes and how what that means in terms of where the electrons cannot be. And then we'll look at different ways of representing orbitals using electron density plots, contour diagrams, and boundary surfaces. So let's talk about first degeneracy. So if we look at the hydrogen atom, remember how we talked about earlier, we looked at the energy diagram and we looked at how the energy between the first and the second level made up about 75% of the total energy change that's possible, and that the energy levels get progressively closer and closer to each other as we go up in energy level. We also talked about now we understand that within a given shell, there could be multiple orbitals. So within the first shell, we only have the one orbital that's in the 1s subshell. However, in the second shell, we can have 2s orbitals, we can have a single 2s orbital, and then 3 of the 2p orbitals. That comes again from the combination of the n, l, and m sub l values. All 3 of those combined gets us one orbital. So we have 2s with an m sub l value of 0, and then we have the 2p where we can have -1, 0, or +1. So each one of these boxes represents one orbital. Within a given shell, all of the orbitals in that shell have the same energy. This is because the energy for the hydrogen atom's orbitals are determined only by the principal quantum number. And this comes from what we learned from the Bohr model. The Bohr model said that the energy of the electron is related to the Rydberg constant over the n value squared. So it's only a function of the principal quantum number n that determines the energy. Therefore, within the hydrogen atom, orbitals of the same shell are degenerate. So that means then that the 2s and the 2p orbitals are the same energy level. That means that the 3s are equal to the 3p and the 3d. That means that the 4s are equal to the 4p, are equal to the 4d, which are equal to the 4f in terms of energy level. So if you put an electron from the 1s up to the 2s, that's the same energy as if you took the 1s to one of the 2p. Okay, so hydrogen's orbitals within the same subshell the same shell are degenerate. Now let's take a look at some ways to represent the orbitals and nodes. So these graphs here, these are called electron density plots. Remember how we said that the wave function squared, that's equal to the electron density, the probability distribution of finding a given electron in a given region. And so what we see is that the electron density, if you take the electron density plots and you rotate them into 3 dimensions, you get these 3-dimensional plots. There are certain regions that are of low density, and in fact even 0 density. Those occur when the probability distribution reaches a value of 0. We call that region of 0 probability a node. This is where there's no electron density, and therefore there's no possibility that the electrons can be there. There is a pattern. That pattern is that the total number of nodes is equal to n-1. So if we have an n value of 1, there are no nodes. For an n value of 2, there is 1 node. For an n value of 3, there are 2 nodes. And you can see here, there are no regions where the electron density reaches exactly 0. It gets very, very close to 0 off at the ends, but it never actually reaches 0. And so there's no nodes. For the 2s type orbital, we see that there is a region where it reaches 0. And it's hard to tell in the electron density plot. It looks like there are 2 nodes, but when you look at it in the 3 dimensions, we see really it's just a radial node that starts and goes all around the sphere there. We then have 2 radial nodes that are at 2 specific distances for the 3s orbital, corresponding to the 2 nodes indicated there. We can also look at the electron density plots and the pointillist plots for p-type orbitals. Here in the 2 p-type orbital, we have one node. This, instead of being a radial node, this is a planar node, which means that it goes all along a specific plane. You'll notice in the 3 p-type orbital that we have two different nodes. Again, because we have n equals 3, we have 2 total nodes. So we have this planar node, but then we also have a radial node. That we see indicated here. These are contour diagrams. These are different ways of representing the orbitals. And so we have a planar node. In both cases, here it's indicated along the x-axis. And then there's also a radial node indicated here in the 3p type orbital. And so we see that there's different ways to represent the orbitals. The most common ways that you'll want to be thinking about them is this way here, the pointillist distribution. And then another way that we commonly represent them is using these boundary surfaces. The boundary surfaces, they represent where there's approximately a 95% probability of finding those electrons. And so we have p-type orbitals that are represented here, and then d-type orbitals that are represented on the right. You'll notice that for the p-type orbitals, that they're the same shape, just in different orientations. Okay, one that goes from end to end along the x-axis, one that goes from end to end along the y-axis, and then one from end to end along the z-axis. For the d-type orbitals, you'll notice that there are 2 general shapes. This one here that looks kind of like a 4-leaf clover, looks as we would call it a 4-leaf clover, and then this one that looks kind of like a p-type orbital with a donut around the middle. In all of these cases, you'll notice that when we look at the nodes, they have a value of n minus 1. So here our n value is 2, and so we have 1 node. The planar node is depicted there. For n equals 3, we have 2 nodes. And here we have 2 planes. In the case of 4 of the different 3D, and then we have these nodes that are indicated here for the 3D Z type orbital. Okay, there are 4 different orbital names and types that you need to be familiar with. The shape of the s orbitals are spherical. Those we saw here indicated. These are the s-type orbitals. Okay, the p-type orbitals, those are dumbbell-shaped. The d-shaped orbitals are cloverleaf, and then a dumbbell with a donut. And then the f-type orbitals, you actually don't need to be familiar with because they get rather complicated. And so in terms of recognizing, you need to be able to recognize the s, the p, and the d type orbitals. Okay? And then if we, as a reminder, if we look at the L values, that would be an L value of 0, 1, 2, and 3. The number of orbitals, as a reminder, that comes from the values of combining n and L and m sub L. So because our m sub L values range from negative L to L, with an L of 0, we can only have 0 for our m sub L value. Here, negative 0, 1, and 0. negative 1, 0, and 1, negative 2 through positive 2, and negative 3 through positive 3. All right, let's practice here. Which pictures represent orbitals with a n value of 2 and an L value of 1? So remember that n tells us about the shell and indicates information about the size and the energy. It's going to be somewhat hard to tell that from an image. So your best piece of information here is to look at the L value. Since we know L equals 1, that corresponds to a p-type orbital, or a dumbbell shape. Okay? So that would correspond to 2 and a 4, giving us an answer of B. Now, what are the other shapes that are there? This you should be able to recognize as an S-type orbital. And then 1 and 3 are both D-type orbitals. In order for us to have an S-type orbital, we would have to have an L value of 0. For a D-type, you would need an L value of 2. Now, question of, do you need to know these designations? Not really. Especially for the D-type orbitals, we're not going to expect that you'd be able to identify, is it a D, is it a dz squared, is it a dx, x squared minus y squared, etc. For the P-type orbitals, the letter designation tells you the axis along which it aligns, and so that's rather easy to determine. But that's not mandatory information. I'll get rid of this writing on here just so you can see. This is just indicating what we've already talked about in terms of which quantum numbers the letters represent the names. Okay, let's try another one. Go ahead and pause this on your own, or pause this and then try this one on your own first. Welcome back. So we want to know which orbital has the fewest nodes. Well, remember that the number of nodes is equal to n minus 1. So if we're talking about an orbital in the lowest energy S subshell, that would be a 1s. N equals 1, and so we have 0 nodes. The lowest energy P subshell would be a 2p, and so that would have n equals 2 and 1 node. And then the lowest energy D subshell is going to be a 3d, and that has an n value of 3 and 2 nodes. So that would mean then that the answer to that is A. A has the fewest nodes, 0. Okay, try this one on your own as well. Welcome back. All right, let's talk about this together. So we want to know if this is for hydrogen atom, we want to rank them in terms of increasing energy. Remember that when it comes to the hydrogen atom, that only the n value determines the energy. And so if we draw our roughly to scale hydrogen atom energy levels, we know that here we would have n equals 1, so this would be the 1s. These would be our 2s and our 2p subshells, our 3s, 3p, 3d, and then our 4s, 4p, 4d, and 4f. So if we want to rank these in terms of increasing energy, this set is going to be our lowest. So we can eliminate A and D. 1 and 3 are equal to each other because they have the same principal quantum number. So 1 and 3 are equal to each other. And 4 is the highest energy level. So that gives us an answer of B. A follow-up question. Which subshell do each of these belong? Well, remember, to designate the subshell, we have to define the N and L value. So go ahead and try that. Welcome back. Hopefully, by looking at this, you were able to pair these up. This is when L equals 2, that's a d orbital, so that gets us a 3d subshell. When L equals 0, that is an s orbital, so that's a 2s subshell. When L equals 1, that is a p-type orbital. And so that would be a 3p and then a 4p type orbital. Okay, that's it. Thanks for watching. Have a great day.